Sp2 hybridization. Sp2 hybridization. One s orbital and two p orbitals of an atom mixed together or hybridized together to form three identical hybrid orbitals is known as Sp2 hybridization. What is Sp2 hybridization? One s orbital and two p orbitals of an atom mixed together or hybridized together to form three equal identical hybrid orbitals is known as Sp2 hybridization. One s orbital is in spherical shape. Two p orbitals, these two p orbitals are in dumbbell shape, each p orbital is a dumbbell shape, and two p orbitals of an atom is perpendicular to each other with 90 degrees. So these s orbital and two p orbitals mixed together to form three identical hybrid orbitals. Here one s orbital and two p orbitals. That means how many orbitals are mixing? Three orbitals are mixing. So they will form three hybrid orbitals. According to theory of hybridization, the number of orbitals that take part into hybridization are equal to the number of orbitals that formed due to hybridization. So these three hybrid orbitals are in planar trigonal shape with an angle of 120 degrees. They are in one plane. All the three orbitals are in one plane. One orbital is like this, other orbital is like this, and third orbital is like that. The three hybrid orbitals are in one plane with an angle of 120 degrees. Now each Sp2 hybrid orbital will have 2/3 of p orbital characters, that is 66.67% p orbital characters, and 1/3 s orbital characters, that is 33.33% s orbital characters. That means the hybrid orbital will have neither s orbital characters nor p orbital characters. It will have a new characters. Those characters, 2/3 of those characters belongs to p orbital and 1/3 of those characters belong to s orbital. Once again, Sp2 hybridization. Sp2 hybridization means one s orbital and two p orbitals of an atom mixed together or hybridized together to form three identical hybrid orbitals is known as Sp2 hybridization. In Sp2 hybridization, three hybrid orbitals are formed, and those three hybrid orbitals are in planar trigonal shape with an angle of 120 degrees. An angle of 120 degrees, and all the three orbitals are in one plane. Each hybrid orbital is called as Sp2 hybrid orbital. This Sp2 hybrid orbital will have 2/3 of p orbital characters, that is 66.67% p orbital characters, and 1/3 33.33% s orbital characters. The examples in which this hybridization is involved is Bf3, boron trifluoride, BCl3, boron trichloride, and ethylene C2H4 or ethene C2H4. These are the important molecules in which we can observe this Sp2 hybridization. Bf3 molecule. In Bf3 molecule, one boron atom is bonded with 3 fluorine atoms with a covalent bond. The X-ray studies of Bf3 molecule reveals that boron atom is present in the center and 3 fluorine atoms are bonded with a covalent bond like this, and the bond angle is found to be 120 degrees and the molecule is in planar trigonal shape. This is the structure of boron trifluoride. So let us observe the formation of this Bf3, boron trifluoride, in the light of this Sp2 hybridization. In Bf3 molecule, the central atom is boron. The atom which is present at the center of the atom is said to be central atom. Central atom is boron. The atomic number of boron is 5. So the electronic configuration of boron is 1s2, 2s2, 2p1. This is the valency shell of boron. In the valency shell of boron, we have 2 electrons in 2s orbital and 1 electron in 2p orbital. On excited state, the electron that was present in the 2s orbital will move to 2p orbital, so that the electronic configuration of boron is found to be 2s1, 2p2. That is, in the valency shell of boron, we have 1 2s orbital, half-filled 2s orbital, and 2 half-filled p orbitals. This is the electronic configuration of boron in its excited state. This is the electronic configuration in its ground state. Here this is excited state. Now this boron atom is undergone to Sp2 hybridization to form 3 Sp2 hybrid orbitals. And these 3 Sp2 hybrid orbitals are in one plane with 120 degrees angle. Now the 3 valency electrons of boron, which are present in the valency shell of boron, when enter in these orbitals, each Sp2 hybrid orbital is filled with 1 electron each, that is half filled with 1 electron each. Now fluorine atomic number F, Z is equal to 9. Electronic configuration is 1s2, 2s2, 2p5. This is the valency shell of fluorine. So in the valency shell of fluorine, you have 2 electrons in 2s orbital and 5 electrons are in 2p orbital. 1, 2, 3, 4 and 5. That means one half-filled p orbital is present in fluorine. So the half-filled p orbital of fluorine overlaps with half-filled Sp2 hybrid orbital of boron to form B dash F sigma bond. This is F and this is B. B dash F sigma bond. The second fluorine atom, half-filled p orbital, overlaps to the next Sp2 hybrid orbital of boron, and by mutual sharing of a pair of electrons forms another B dash F sigma bond, and the third fluorine atom will overlap here and by mutual sharing of that pair of electrons forms B dash F sigma bond, so that 3 B dash F sigma bonds are formed in Bf3 molecule. So the Bf3 molecule is in planar trigonal shape with bond angle 120 degrees. This is planar trigonal. Planar trigonal. That means triangular with 120 degrees angle in one plane. So this is the structure of Bf3 molecule. Similarly, we can explain the structure of BCl3 also. You know the electronic configuration of chlorine, Cl, is 17. That is 1s2, 2s2, 2p6, 3s2, 3p5. So this is the valency shell. So just like the valency shell of fluorine, 2s2, 2p5, here we have 3s2, 3p5. So here also we have a half-filled p orbital of chlorine, 1, 2, 3, 4, 5. So in fluorine, this is half-filled p orbital, 2p orbital. But in BCl3 molecule, chlorine will have half-filled 3p orbital. That is the only difference. The whole structure is same. These are the formations of Bf3 and BCl3. Similar way, instead of fluorine, here you will have chlorine. It's all. This is also chlorine and this is also chlorine. Then it becomes the structure of BCl3. Both are in planar trigonal shape with an angle of 120 degrees. C2H4, ethene molecule. The X-ray studies of ethene molecule shows that two carbon atoms are bonded with a double bond and each carbon atom is bonded with sigma bonds with 2 hydrogens each. And the bond angle here is found to be 120 degrees. So, this is the structure of C2H4, which we have an experimental evidence for this structure. Now let us verify how this molecule is formed in the light of this Sp2 hybridization. Remember, this hybridization is a hypothetical theory. The structure of molecule has evidence. To support that evidence, we are giving a scientific explanation for the formation of that molecule. Here you should not give the logical thinkings, the why and how, why it should not be like that. You should not argue like that, because this theory of hybridization is purely hypothetical theory. This theory was proposed to support the facts that were present in the molecule. So let us verify how Sp2 hybridization is involved in carbon. In this C2H4 molecule, you may observe that 2 carbon atoms are present as central atoms and 2 hydrogen atoms are bonded with a covalent bond, and in between carbon and carbon we have a double bond. The presence of double bond can be proved by its bond length and bond energies, because if C double bond C is there, which we see in ethane, there the bond length is found to be 1.54 angstroms, whereas here the bond length is found to be 1.34 angstroms, and the bond energies is also different. That's why bond angles, bond energies and bond length shows that there will be a double bond between 2 carbon atoms. Now we are explaining how that double bond is possible in it. So here we have 2 carbon atoms as central atoms. The electronic configuration of carbon is 6. 1s2, its electronic configuration 1s2, 2s2, 2p2. That is, in the valency shell of carbon, we have 2 electrons in 2s orbital and 2 electrons in 2p orbital. This is electronic configuration of carbon in ground state. This is ground state electronic configuration. On excited state, the electronic configuration of carbon is found to be 1s2, 2s1, 2p3. That is, in the valency shell of carbon, we have 1 electron in 2s orbital and 3 electrons in 2p orbital. Now here we have 4 half-filled orbitals. One is 2s orbital and other 3 are 2p orbitals. Now the carbon will undergo to Sp2 hybridization. Now you have to remember, once again I reflect, You should not ask me why the third p orbital is not take part. You should not raise a logical question. I have no answer for it because I am claiming this sp2 hybridization in carbon to support its structure where structure has an experimental evidence. This structure is possible only when this is possible. That's why you have to satisfy with my argument. You should not ask me why that p orbital is not involving. Since the p orbital is not involving, for that only the reason to have this structure in C2H4. So when this carbon is involved in sp2 hybridization, what happens? 3 sp2 hybrid orbitals will be formed. Now 3 valence electrons of carbon will enter here. What about the 4th electron and 4th orbital? Because they are in one plane. They are in one plane. Now that p orbital, which is not take part into hybridization, is perpendicularly arranged to this. Because if they are in one plane like this, the 3 orbitals are like this. Perpendicular to these 3 orbitals, the pure p orbital is present like this. Since it is not possible for me to draw, I will draw like this. Actually, they are arranged like this. So this is the pure p orbital which is not involved in this hybridization. This pure p orbital is also having 1 electron. So this is the position of carbon. 3 sp2 hybrid orbitals with half-filled electrons and 1 pure p orbital with half-filled electron. And these 3 hybrid orbitals are in one plane in planar trigonal shape, and the pure p orbital is perpendicular to this. This is the position of 2 carbon atoms in ethane. Now let us verify how the molecule is forming. So half-filled p orbital of 1 carbon atom overlaps with half-filled p orbital of another carbon atom. So let it be 1 carbon. This is also 1 carbon. By mutual sharing of a pair of electrons forms C dash C sigma bond. C dash C sigma bond. Now in this carbon you have 2 more sp2 hybrid orbitals which are also half filled. And in this carbon you have 2 sp2 hybrid orbitals which are half filled. Now these half filled sp2 hybrid orbitals overlaps with half filled 1s orbital of hydrogen to form C dash H sigma bond. Such 2 bonds are formed. This carbon will also form 2 sigma bonds with 2 hydrogen atoms, so that here also you will have 2 C dash H sigma bond, so that you will have CH. The bond angles are 120 degrees, any bond angle. Now, what about this p orbital? Here in this carbon, we have 1 p orbital, half filled p orbital. Now only these 3 orbitals are involved here. So on each carbon we have a pure p orbitals, half filled pure p orbital, and they are perpendicular to this plane. This is one plane, they are in one plane, and the pure p orbitals are like this, perpendicular. That means they are parallel to each other. These parallel p orbitals with opposite spins laterally overlaps to form a pi bond between carbon and carbon, so that you will have 1 sigma bond and 1 pi bond between 2 carbon atoms. That's why its bond angle was 1.34 angstroms and bond length is 1.34 angstroms and bond angle is 120 degrees. In C2H4 molecule, we have 1, 2, 3, 4 and 5. 5 sigma bonds are there and 1 pi bond is there. In C2H4 molecule as a whole we have 5 sigma bonds and 1 pi bond. This is the structure of C2H4 molecule. Sp hybridization, when one s orbital and one p orbital of an atom mixed together or hybridized together to form two identical equal orbitals is known as Sp hybridization. One s orbital and one p orbital of an atom, that means belonging to same atom, mixed together to form two identical hybrid orbitals is known as Sp hybridization, and the orbitals are called as Sp hybrid orbitals. Let us see. One s orbital and one p orbital mixed together to form two identical hybrid orbitals is known as Sp hybridization. And these two hybrid orbitals are in linear shape with an angle of 180 degrees. With an angle of 180 degrees. Each hybrid orbital will have half of s orbital characters and half of p orbital characters, that is 50% s orbital characters and 50% p orbital characters. Half of s orbital characters. These two hybrid orbitals are linearly arranged at 180 degrees angle. The molecules which is involved in this hybridization are BeCl2, beryllium chloride, and ethyne C2H2, common name is acetylene, and carbon dioxide CO2. These are the important molecules which are involved in this Sp hybridization. Sp hybridization, when one s orbital and one p orbitals of an atom mixed together or hybridized together to form two identical hybrid orbitals is known as Sp hybridization, and the orbitals are called as Sp hybrid orbitals. Each Sp hybrid orbital will have 50% its orbital characters and 50% p orbital characters, and they are arranged in a linear shape with an angle of 180 degrees. Now let us verify the structure of these molecules in which Sp hybridization is involved. Let us observe the formation of BeCl2 molecule. The BeCl2, beryllium chloride. BeCl2 is beryllium chloride. This X-ray study shows that the beryllium chloride molecule is in linear shape with an angle of 180 degrees. With an angle of 180 degrees. It shows that beryllium is present at the center of the atom and two chlorine atoms are arranged to it on both the sides. Now let us verify the structure in the light of this Sp hybridization. In BeCl2, the central atom is beryllium. Its atomic number 1s2, 2s2. That means in the valency shell, you have 2 electrons in 2s orbital. In the second energy level, we have 2p orbital. Here, that 2p orbital is empty. According to this electronic configuration, beryllium is not supposed to take part into any type of bonding according to octet rule. Because according to valency bond theory. Because what valency bond theory tells us? Only half-filled atomic orbitals will involve into chemical bonding. But here there is no half-filled orbital. But beryllium is found to form 2 bonds. How is it possible? It is possible only when beryllium has its electronic configuration like this. That is, its electronic configuration in excited state should be 2s1, 2p1. That is 1 electron in 2s orbital and 1 electron in 2p orbital. The half-filled p orbital is there. Now one 2s orbital and 2p orbital. In the formation of this BeCl2 molecule, this beryllium will undergone to sp hybridization to form 2 sp hybrid orbitals. These 2 sp hybrid orbitals are in linear shape with an angle of 180 degrees. The 2 valence electrons that are present in the beryllium will occupy in these 2 hybrid orbitals. This is not p orbital. Remember, this is one sp hybrid orbital and this is another sp hybrid orbital. The both are in linear arrangement. Each orbital is half filled with 1 electron each. Now if you take a chlorine electronic configuration, ClZ is equal 17, will have configuration as Ne 3s2 3p5. That is, in the valency shell of chlorine you have 2 electrons in 3s orbital and 5 electrons in 3p orbital. 1, 2, 3, 4 and 5. So here we have one half filled p orbital. So in each chlorine atom we have half filled p orbital. So the half filled p orbital of beryllium, half filled p orbital of chlorine overlaps with half filled sp hybrid orbital of beryllium, and by mutual sharing of that pair forms one sigma bond between beryllium and chlorine. This is one sigma bond, Be-Cl sigma bond. Now the second chlorine atoms half filled p orbital overlaps with half filled sp hybrid orbital of beryllium, and by mutual sharing of one pair forms Be-Cl sigma bond, so that 2 Cl sigma bonds are formed between beryllium and 2 chlorine atoms, and these 2 sigma bonds are in linear shape with 180 degrees angle. So the molecule is in linear shape with an angle of 180 degrees. This is the molecular structure of BeCl2.